Here's one. Look at this. Nice data points. Nice smooth line drawn through it. Here's some nice data points and smooth line drawn. But look at this. This line goes out here. The data point's down here. What do you notice about the uncertainty bars on these? Have you noticed any uncertainty bars yet?
Very small.
Very small. I'm a bit skeptical of that. Relay feedback. Okay, all those so far have been, you get a number of data points, you get a number of different sine frequencies, and you do that amplitude ratio and the phase angle, and you plot them. You with me? Now, look at relay response. They do one experiment. That's all they have to do. These alternate people got it easy. One experiment. This is a nice experiment. This is the input, relay feedback input. This is the output. Here's the set point when the relay feedback is above the set point. The input is at 55. When the relay feedback goes below the set point, the input changes to 35. This is temperature, so it's exactly opposite of other things that you know. So when the input goes down here, the temperature starts rising, and it goes down again, and these things. This is beautiful. Yeah, the degree C here. So this is the ultimate period, which is the reciprocal of the ultimate frequency. So here's an ultimate frequency of 8.7. The student learned that just by doing one experiment instead of 6 or 8 or 10. Sweet. And got a KCU of 66.44 plus or minus 9.70. You know what? 60 or 70 would be fine with me instead of 66.44. No, I'm no advocate of a lot of significant figures. Here's another one experiment. This one is airflow, so it looks the other way. As the output goes high, the input goes down. When the output goes down, the input goes high. So this is continuous oscillation. Here's another one, pressure system. Another one, don't know what this is. Oh, it's pounds per minute. So it's one of the flow systems. Here's another one. Don't know what system that is. Here's another one. Oh, let me talk about this one. Average KCU. KCU is, there's a formula for it. It's 4, this should be pi, so something wrong. It's 4 over pi multiplied by the delta M over the delta C. So that's what's plugged in there. Delta M has what units for any of your system? Percent. Who said that? Good, Caleb. Delta C for this system has what units? Can you tell, Joe? Pounds per minute. So if delta M is percent and delta C is pounds per minute, what are the units of this going to be? Percent per pounds per minute. So the units are upside down. I suspect the KCU is upside down, but I wouldn't guarantee that. You remember I sent you an email that said the units of the KC are the reciprocal of the units of the K. The controller has reciprocal units from the system. Would you like me to tell you more about that?
Yes.
block diagram here. Focused yet? All right. This is our system. I'm going to add something to this system. This has units of K. Might as well write the whole transfer function here. K e to the minus T naught S over RS plus. I'm going to draw something else in there. They might say, wow, Dr. Henry, we're putting a controller on this thing.
Wow, Dr. Henry, we're
We're actually going to do that in a week or so. But this is what we're figuring out right now. The controller has a transfer function also. So I'll tell you what the controller transfer function is.
Yes. Yes, sir.
Well, it's going to be hard for you. That's it. The controller transfer function is a constant. And it is Kc. Not with a subscript u, but it's Kc. And have you seen this diagram before? Have I done it? All of you answer at once. Have you seen this before? Have I done this before?
No, this class. No.
Okay. I'm going to do it now. This is a block diagram of a feedback control system. Somebody used the word feedback today. Was that you, Nathan? Nathan said that something or other in the economy is a feedback system. Imagine that. This is a feedback control system. I think we call it a feedback because you take something here and you go over here with it. Does that sound right?
Yes.
Who said yes? Good, Jerry. Now, the units of this thing here are whatever they are. Let's say percent centigrade right now. This diagram represents the flow of information. So this is the temperature of this output, degrees centigrade, Celsius. Comes over here. What are the units of it when it gets over here? Same. They don't change units. Nothing changes when you're going through a wire like this or through a line like this. And then this minus sign means we subtract this from this thing. This thing here is the reference point, aka the set point. So let's say the temperature in this room, let's say it has a set point of 72 degrees. That would be in Celsius, let's say 16 degrees Celsius. I just sort of made that up in the drawing. I think it's 16. Anybody know what 72 Fahrenheit is in Celsius? 20? No way. Huh? You're just guessing like I am, aren't you? 22? Who really knows how to translate from...
22.22.
How much?
I would convert it.
22.22. Will you mind if I just say 22?
I'll let it slide.
Huh?
I'll let it slide.
Okay. Now then, the units of this have to be the same as the units of the output because we're going to do a subtraction operation here. Just like you can't add apples and oranges, you can't subtract oranges from apples. So this is that, this is that. And then there's this thing here. What are the units of this thing? This is equal to what you get when you subtract this from that. This is the output of this little thing. It's called a summation block, or summation, whatever. Summation point. And this is called a pickoff point. Indeed, it was called a pickup point, but it's not. It's called a pickoff point. All right. Have you seen these before? Huh? I haven't talked to you about it, have I? But maybe somebody else has talked to you about these things? Okay. What does this letter E stand for?
Some.
The letter E. Who said error? Oh, Caleb. Somebody else over here say error? It's the error. It means the difference between what the reference is and what the actual is. Can the error be negative?
Sure.
Can it be positive? It can be either one. The error goes into the controller, and the controller then, based on the error, decides what to do with the manipulated variable to make the system produce the right value of the output. That's what we're designing. We're designing feedback controller. The formula for the controller is you take this and you multiply it by that and it gives you this. That's really complicated. This is called a proportional only controller. It was the one we're going to study for a couple of weeks. And what it means is the output is proportional to the error. And the control engineer, KC is always positive. Oh, I shouldn't have said that, because in the temperature system it's negative, but let's ignore that small detail. It's always positive or negative if the slope of the SSOC goes the other way. But it's always a constant. But there's a maximum value that it can have. Does anybody know what we would call the maximum value that it can have?
Would it be the maximum value?
What is the maximum value of the controller gain? That's the controller gain. K means gain. Everybody say K means gain, Dr. Henry.
K means gain, Dr. Henry.
So without any subscript, it means the gain of the system. Say that. If it has a subscript C, it means it's the gain of the
Controller.
Oh, good. Trying to make this so that you can understand it. You with me, Ronnie? What's the largest value that you can have for the gain of the controller? Wrong. K.